On a mountain, there are n square poles which are designed to use for transportation, by using cable cars. All the poles, in the mountain, are located at different altitudes. Now, using these poles, two companies, A and B, offer a transportation service, such that each company uses exactly K cable cars, and where each cable car transfers from a lower pole to a higher one, with no intermediate stops. The companies also ensure that the K cable cars will have K different starting points and K different ending points, and such that a cable car which starts higher also finishes higher. Let us take the example of the illustration, where n is equal to 3. That is, we have 9 poles in this case, and let us assume also that K is equal to 5. In this example, the 5 cables of the first company are drawn in orange. The cables of the second company are drawn in blue-red. Let us now look at the following 2 emphasized poles. Observe that one can reach from the lower emphasized pole to the higher one by using the cables of the first company. However, one can also reach from the lower to the higher emphasized pole by using cables from the second company. In this case, we say that companies A and B share a common transportation. Let us now look at the example where n is equal to 4. That is, we have 16 poles. And let us assume also that K is equal to 9, that is, each company uses 9 cables. Again, in the illustration the cables of the first company are drawn in orange, and the cables of the second company are drawn in blue-red. In this example, we again have the situation where one can reach from the lower to the higher emphasized poles by using cables from both companies. That is, companies A and B share a common transportation. This brings us to the main question in this challenge. We have the following main problem. Find the minimum value of the number K of cables that will guarantee a common transportation for the companies A and B, no matter how these companies arrange their cables. To find the solution to our problem, let us first look at the following example, where we consider n square poles which are represented by the red points. To guarantee that each red point will have a different altitude, we perturb the red points as in the illustration. Let the red and the green segments be the cables of the first and the second companies, respectively. We observe that each starting point which is located higher also finishes higher, and thus our construction is valid. We also observe that in this case, companies A and B have no common transportation. This is because company B only connects points which are on a line which is vertical, while company A only connects points which are on the same diagonal. And it can be easily seen that in this case, K is equal to n square minus n. In conclusion, the minimum number K that we are seeking is greater than n square minus n. Observe also that in our example, we cannot add even one more cable to either company. Indeed, otherwise the number of cables will be greater than the number of starting points, which is against our assumption. This may suggest that if K is equal to n square minus n plus 1, then we must have a common transportation. We will prove next that this is indeed the case, and this will answer the main question in this challenge. To show this, we associate the poles and cables, in our problem, to the vertices and the edges of a graph G, respectively. We observe that each connected component of G is a simple path. Since if two paths have middle vertices in common, then this essentially means that the number of cables is greater than the number of starting or ending points, which is against our assumption. Now we claim that if the number k of cables is equal to n square minus n plus 1, then G has exactly n minus 1 connected components. Indeed, let us assume that we have L connected components. And let us assume that we have Ni vertices at the ith connected component. This immediately implies that the number of edges in the ith connected component is equal to Ni minus 1. Hence, we obtain the following equality, where both sides represent the number of edges in our graph. However, observe that the sum, in the left-hand side, is the number of vertices, which is equal to n square. Thus we obtain that the number L of connected components is equal to n minus 1, as needed. Now, if we associate the cables of companies A and B, respectively, to the graphs G and H, then companies A and B share a common transportation, if and only if the graphs G and H have connected components G tag and H tag, respectively, which have two vertices in common. We assume that both G and H have n square vertices, and the number of edges is equal to n square minus n plus 1. Hence, as was proved previously, both G and H have exactly n minus 1 connected components. Observe that G has at least one connected component, G tag, with at least n plus 1 vertices. Since otherwise the number of vertices of G is smaller than n square. Hence, since H has n minus 1 connected components, it follows by the pigeonhole principle that G tag shares at least two vertices with some connected component of H. This proves our main assertion, and thus our proof is finally complete.